An experiment performed today yields the exact same physical results when repeated tomorrow. This temporal uniformity is not merely a passive property of nature, but the active mathematical root of energy conservation. Abstract algebra bridges geometry and physical dynamics by mapping continuous transformations to algebraic structures. Mathematician Emmy Noether discovered that every differentiable symmetry of an action functional corresponds to a specific conservation law. To understand the mechanism, we define the action functional as the integral of the Lagrangian over time. The Lagrangian is a function characterizing the system, defined as kinetic energy minus potential energy. Physical systems evolve along paths that minimize or extremize this action functional. This fundamental principle of least action states that the first variation of the action along the true path is zero.
Evaluating this zero variation condition mathematically generates the Euler-Lagrange equations. These differential equations govern classical trajectories, equating the time derivative of conjugate momentum to the generalized force. Continuous symmetries are formally modeled using Lie groups, where elements vary smoothly rather than discretely. Unlike static reflection symmetries, Lie groups allow for transformations that are infinitely close to doing nothing. We define a continuous symmetry transformation acting on the generalized coordinates of a system. A transformation is a symmetry if it leaves the form of the Lagrangian invariant up to a total time derivative. We isolate the behavior of the system under an infinitesimal transformation by expanding the group element around the identity. The coordinates shift by a tiny parameter epsilon multiplied by a specific generator function.
These generator functions form the basis of a Lie algebra, representing the tangent space at the identity element of the continuous group. They dictate the direction of the coordinate shifts under smooth transformations. When an infinitesimal transformation shifts the coordinates and velocities, the resulting variation of the Lagrangian is computed using the multivariable chain rule, focusing on partial derivatives with respect to coordinates and velocities. The total variation of the Lagrangian equals the partial derivative with respect to position times the position shift, plus the partial derivative with respect to velocity times the velocity shift. Next, we substitute the Euler-Lagrange equations directly into this variation expression. This replaces the explicit partial derivative with respect to position with the total time derivative of the generalized momentum.
By applying the product rule for differentiation in reverse, we combine the terms into the total time derivative of a single product, generalized momentum multiplied by the coordinate transformation generator. Because the transformation is a strict symmetry, the variation of the Lagrangian must vanish, or equal a total time derivative of a gauge function, forcing the remaining time derivative expression to equal zero. Any quantity whose total time derivative is identically zero remains perfectly constant during the evolution of the system. This invariant expression is known as the Noether charge, the conserved physical quantity. Let us apply this exact derivation to time translation symmetry. If a physical system is invariant under shifts in time, its Lagrangian contains no explicit time dependence, meaning its partial time derivative is zero.
Shifting the time coordinate infinitesimally alters positions and velocities. The generator function for this temporal translation corresponds precisely to the total time derivative of the generalized coordinate itself. Substituting this temporal generator into the Noether charge formula yields the generalized momentum multiplied by velocity minus the Lagrangian. This exact mathematical construction defines the total energy of the physical system. Because the laws of nature do not change from one moment to the next, the time translation group guarantees that total energy is perfectly conserved in every closed physical system. Now examine spatial translation symmetry, represented algebraically by the real vector space group under addition. This implies that performing an experiment in one location yields identical results to any other location.
The generator for a spatial shift alters the position coordinates by a constant uniform displacement vector. The corresponding Noether charge isolates the partial derivative of the Lagrangian with respect to velocity. This partial derivative defines linear momentum. Because space is completely homogeneous, the total linear momentum of an isolated physical system is conserved along the direction of that spatial translation symmetry. Rotational symmetry introduces the special orthogonal group in 3 dimensions, denoted as SO3. This Lie group represents rotating the entire coordinate system without changing any lengths or relative angles. The generators of the Lie algebra for the group SO3 are skew-symmetric matrices, representing infinitesimal rotations around the spatial axes. They cross-multiply the position vectors with the velocity vectors.
Plugging these rotational generators into the Noether formula produces the cross product of the position vector and the linear momentum vector. This conserved quantity is precisely defined as angular momentum, showing how rotating an experiment does not alter its basic physical behavior. Isotropy of space, meaning all directional vectors are physically equivalent, directly dictates the conservation of angular momentum. This algebraic invariant stabilizes the orbits of massive planets, controls the behavior of quantum spins, and guides the orientation of spinning navigational gyroscopes. Moving beyond discrete point particles, we apply Noethers theorem to continuous physical fields. In field theory, the standard Lagrangian is replaced by a Lagrangian density integrated over a 4-dimensional space-time volume, tracking variables smoothly across every point in space and time.
The continuous symmetries of smooth space-time transformations are combined into the Poincaré group. This fundamental structure merges space and time translations with relativistic Lorentz transformations, containing both constant velocity boosts and 3-dimensional spatial rotations within a unified framework. Invariance under the full continuous Poincaré group generates a conserved rank 2 tensor field. This critical algebraic object is known as the canonical energy-momentum tensor, describing the local density and flux of energy and momentum across the space-time continuum. The divergence of this energy-momentum tensor is exactly 0, mathematically packing the individual conservation laws of energy, linear momentum, and angular momentum into a single elegant relativistic equation that holds true across classical electrodynamics and general relativity.
Noethers theorem also extends beautifully to internal symmetries, where algebraic transformations alter the internal attributes or components of a field, rather than changing the coordinates within physical spacetime. This marks the transition from classical kinematics to modern quantum field theory. The fundamental internal symmetry is the unitary group U1, consisting of complex phase rotations on a unit circle. Complex-valued quantum fields, such as those describing electrons, exhibit absolute independence regarding this global phase choice across the entire universe. Shifting the phase angle of a complex scalar field by a constant value leaves the field Lagrangian density completely invariant. The resulting conserved Noether current represents the local physical flow of charge, ensuring that the total net change within a boundary matches the outward flux.
Integrating the time component of this Noether current over all space reveals that global U1 phase symmetry is the precise mathematical source of the conservation of electric charge, proving that charge conservation is an algebraic property of quantum fields. When we upgrade an internal symmetry parameter from a global constant to a localized function of spacetime coordinates, we transition directly into gauge theories. This means the phase can be rotated independently at every single point in space and time. Local gauge invariance requires introducing compensating vector gauge fields to cancel out the coordinate-dependent variations. This structural necessity directly generates the fundamental gauge bosons, such as photons, which mediate the forces of nature between interacting matter fields. Non-abelian Lie groups, such as special unitary groups SU2 and SU3, govern these localized internal symmetries. Their non-commutative algebra gives rise to weak isospin and strong color charge conservation, defining the weak and strong nuclear forces. In general relativity, diffeomorphism invariance represents symmetry under arbitrary smooth coordinate transformations. This generalized coordinate independence makes defining localized energy conservation exceptionally complex, requiring specialized pseudotensors, because gravitational energy cannot be localized to a single point. When a continuous symmetry of a Lagrangian density is not preserved by the stable vacuum state of the system, spontaneous symmetry breaking occurs. This misalignment between the laws of physics and the lowest energy state produces massless scalar excitations.
These emergent massless excitations are known as Goldstone bosons, demonstrating that even when a symmetry is hidden in the ground state, its algebraic structure dictates physical particle content, as seen in the mechanism behind the mass of elementary particles. Modern particle physics relies entirely on this synthesis, where the Lie groups of the Standard Model dictate all allowable particle interactions through their underlying conserved quantum numbers, constraining how quarks and leptons transmute, decay, and interact. Ultimately, abstract algebra reveals that the conservation laws keeping our universe stable are not arbitrary operational rules, but the unavoidable geometric consequences of continuous symmetries, embedding the deep structural properties of group theory directly into physical reality.